So we got a projectile question here. The ball's initially at rest. It's kicked directly toward a fence, a point 32 meters away, so that is going to be important. It's also clearly labeled on the diagram down here. The velocity of the ball as it leaves the kicker's foot is 20 meters per second. That is the overall velocity. That is also clearly labeled right here. And it's done at an angle of 37 degrees, also labeled on the diagram. The top of the fence is 2.5 meters high. That's labeled on the diagram, and that is going to be important. As soon as you see something like an initial velocity kicked at a certain angle, then you know you are almost definitely going to have to break that velocity vector down into its components. So the very first part here then, let's look at part A. So determine the maximum height the ball reaches. That is a vertical question. So we are going to have to find the vertical component of that velocity. Since it is the vertical side, the opposite side of the triangle, we are going to get it by taking the hypotenuse multiplied by the sine of 37. And they tell you right here that sine of 37 is 0.6. So 0.6 times 20 gives you 12 meters per second as the initial vertical velocity. So we can write that down. Our initial y velocity is 12 meters per second. We know that it is affected by gravity vertically, so its acceleration is negative 10 meters per second squared. We know at the maximum height is the peak, so that is a final velocity of 0 meters per second, and we're looking for the displacement, so the y value there. So another option you have, though, is you can also say that the time to reach the peak, if you shoot it up at 12 meters per second, is 1.2 seconds. So that might actually be a little bit easier route there. Then you can use the fourth equation. And so it will say that the initial y velocity times the time, but this is just going to drop out. Sorry, it's the final y velocity, but that is 0 at the peak in the fourth equation, and so it will drop out. And then you multiply it by minus 1/2 gt squared. So just plug that in there, minus 1/2, gravity is negative 10, the time is 1.2 seconds. Don't forget to square it, and if you work all of that math out, you will get 7.2 meters. The two negatives cancel each other there. So that is part A. So in part B here, it says, assuming there was no fence, determine the horizontal range of the ball. So that is going to be a horizontal question. We got to find the horizontal initial velocity. So to do that, we'll take the hypotenuse, which is 20 meters per second, and multiply it by, since it's the adjacent side, the cosine of 37 degrees. They actually tell you right here, cosine of 37 is 0.8, so 0.8 times 20 is 16 meters per second. So that's how fast it's going to the side, and that's how fast it will go to side the entire problem. So if we want to find the range, we're going to find the x displacement, and you can think of this as the third equation. It's just the initial velocity, which is just the velocity, will never change, times the time, plus all that acceleration stuff, but the acceleration is 0, so it's gone. And so now we can solve in this equation over here. So this is our x velocity. Make sure that that is what you're plugging in there, not 12, not 20, but 16 is the x velocity. And our time is the time to come back down from the ground. We solved on the previous one that the time to the peak was 1.2 seconds. So the total time in the air will be double that, 2.4 seconds. So that is actually the time that we want to plug in here. So when you multiply those two out, you get 38.4 meters to the side. This next one says, determine the time it takes for the ball to reach the plane of the fence. So this is another horizontal question. We know again that horizontally we are going 16 meters per second. We are simply going to use our equation for the definition of velocity. And so that's it. Let's rearrange it to solve for time. And then when we plug in our numbers, the fence is 32 meters away. And horizontally, we are going 16 meters per second. So it's going to take us 2 seconds to cover a horizontal distance of 32 meters. The next one says, will the ball hit the fence? And if so, how far down? If not, how far above will you be? So the important thing is we just figured out on the previous one, I'm going to call it T sub F for the time to the fence. That is 2 seconds. So we want to see where we are vertically now. What's our vertical displacement at that time? So our time is 2 seconds. It's a vertical question. So we know that our acceleration due to gravity is negative 10 meters per second squared. And we actually also know that our initial y velocity, going back to the previous one, was 12 meters per second, if you remember. So now let's find the one that talks about all of these at once. It's the third one again. So the y displacement is the initial y velocity times the time plus 1/2. I'm going to go ahead and write the acceleration as g times t squared. So let's start to plug in. Initial y velocity is 12. The time is 2 seconds to get to the fence. Gravity is negative 10. And the time again is 2 seconds. Don't forget to square it. And so we will get here 24 from this term. 2 squared is 4. Negative 40. Half of that is negative 20. And so we get 4 meters. Now remember what you just solved for here. This is its height when it is 32 meters to the side after 2 seconds. So we have decided that it will not hit the fence, but we also need to do the final step, which is since the fence is 2.5 meters tall, it's going to clear it by 1.5 meters. So that's the real answer that you're looking for there. On to the graphs. So if we look at the horizontal component of the velocity, remember that that will be constant. We solved for it, it's 16. So you probably ought to use a straight edge, which you should keep on you. And so I'm just going to make a little mark here at 16 and then just, whoop, actually made a mistake here because it says until the ball reaches the plane of the fence. That's 2 seconds. So scratch all of that out right there. So straight line at 16 meters per second until you get to 2 seconds there. So what about vertically? So vertically, this velocity is going to change. We know that our initial y velocity is 12, so we're going to start right there. And I actually know that after 1.2 seconds, we get to the peak. So there's a second dot there. So just connect these two up, stop at 2 seconds, and that is what the graph of your vertical velocity will look like. So on to position graphs. So first of all, the horizontal position versus time. It's going at constant speed horizontally, so we should have a straight sloped graph there. And we know after 2 seconds that we get to 32 meters, so I'm just going to approximate it right there, and then use a straight edge and connect to the origin. And so that is what your horizontal position versus time should look like. And so finally, our vertical position versus time here. Now I just realized that I didn't put the time down here and here. So let's just approximate that, about 2 seconds, about 3 seconds, about 4, and this will be 5 seconds here. Since you're accelerating vertically, this is going to be a curved graph, a curved position versus time graph. We know at 2 seconds that the problem ends, and we know at 2 seconds we just solved for that in a previous problem that it was 4 meters high. We also know at 1.2 seconds that we are about 7.2 meters high, so that's right about there. I'm just sketching it to get the basic shape. That's the peak of the parabola, so it should curve up like that and then down and stop there.